Supplementary ground is required when the main grounding system is inadequate to dissipate the fault current or to provide any other required electrical functions. This means that if the existing grounding system cannot handle the amount of current that would flow during a fault, supplementary grounding is needed to ensure that the fault current is safely dissipated, preventing electrical shock or fire hazards. The capacity of a grounding system is determined by several factors, including the size and material of the grounding conductors, the number and type of grounding electrodes, and the soil resistivity. If these factors are insufficient to handle the potential fault current, supplementary grounding is necessary. Additional ground rods or other grounding electrodes are needed to lower the ground resistance to an acceptable level. Ground resistance is the resistance of the earth to the flow of electrical current. A lower ground resistance provides a better path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse more quickly, clearing the fault. Acceptable ground resistance values are typically specified by electrical codes and standards. If the measured ground resistance exceeds these values, additional grounding electrodes should be installed to lower the resistance. The grounding system is being extended to a new area. When electrical systems are extended to new areas, the grounding system must also be extended to ensure that all equipment and circuits are properly grounded. This may involve installing additional ground rods connecting to existing grounding electrodes, or running a grounding conductor to the new area. It's important to ensure that the grounding system in the new area is properly connected to the existing grounding system to provide a continuous and effective ground path. The existing grounding system has been damaged or is no longer effective. Over time, grounding systems can become damaged or degraded due to corrosion, physical damage, or changes in soil conditions. If the grounding system is no longer effective, it may not be able to safely dissipate fault current or provide adequate protection against electrical shock. Regular inspections and testing of the grounding system are essential to identify and address any problems. If damage or degradation is detected, repairs or replacement should be made promptly. Additional grounding is needed to protect against static electricity or lightning. Static electricity and lightning can generate very high voltages that can damage equipment or cause injury. Grounding provides a path for these voltages to safely dissipate into the earth. In areas where static electricity or lightning is a concern, additional grounding may be needed to provide adequate protection. This may involve installing lightning rods, grounding mats, or other specialized grounding equipment. Additional grounding is needed to meet the requirements of a specific code or standard. Electrical codes and standards often specify minimum grounding requirements for different types of electrical systems. These requirements are designed to ensure that electrical systems are installed and operated safely. If the existing grounding system does not meet the requirements of the applicable code or standard, additional grounding may be needed. Firstly, consider the specific application and voltage level. For instance, in residential wiring, the National Electrical Code, or NEC, mandates specific grounding electrode systems based on the service entrance. This typically involves a ground rod, a ground ring, or connection to a metallic water pipe. Supplementing these with additional ground rods might be necessary if the soil resistivity is high. Secondly, consider industrial settings with sensitive electronic equipment. Here, a dedicated grounding system might be required to minimize electrical noise and ensure proper operation. This could involve creating an isolated ground plane and connecting it to the main grounding system at a single point to avoid ground loops. Thirdly, consider telecommunications infrastructure. Proper grounding is crucial to protect equipment from lightning strikes and power surges. In these applications, a combination of ground rods, grounding plates, and bonding conductors is used to create a low impedance path to ground. Fourthly, consider renewable energy systems like solar photovoltaic or PV arrays. These systems often require dedicated grounding electrodes to protect against ground faults and lightning strikes. The NEC provides specific guidelines for grounding PV systems, including the size and type of grounding conductors and electrodes. Fifthly, consider healthcare facilities. These facilities have stringent grounding requirements to ensure patient safety. Equipotential grounding systems are used to minimize voltage differences between conductive surfaces in patient care areas, reducing the risk of electrical shock. This involves bonding all conductive surfaces to a common ground point. Sixthly, consider data centers. Data centers house critical infrastructure that requires reliable grounding to prevent data loss and equipment damage. A robust grounding system is essential to minimize electrical noise and protect against power surges. This often involves a combination of ground rods, grounding grids, and surge protection devices. Seventhly, consider outdoor installations like cell towers and radio antennas. These structures are highly susceptible to lightning strikes, so a comprehensive grounding system is essential to protect equipment and personnel. This typically involves a combination of lightning rods, grounding conductors, and ground rings. Eighthly, consider temporary electrical systems used at construction sites or outdoor events. These systems must be properly grounded to ensure worker safety. Ground fault circuit interrupters, or GSEIs, are often required to protect against electrical shock hazard. The grounding system should be inspected regularly to ensure that it is in good condition. Ninthly, consider agricultural applications like irrigation systems and livestock facilities. These systems often operate in wet or corrosive environments, so a robust grounding system is essential to prevent electrical shock hazards. Ground rods should be driven deep into the ground to ensure good contact with the soil. Tenthly, consider marine environments where corrosion is a major concern. Grounding systems in boats and docks must be designed to withstand the harsh marine environment. This often involves using corrosion-resistant materials and coatings. The grounding system should be inspected regularly to ensure that it is in good condition. The selection of grounding electrodes depends on several factors, including soil conditions, local codes, and the type of equipment being grounded. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. Ground rods are typically made of copper or copper-clad steel and are driven vertically into the ground. Ground plates are made of copper or other conductive materials and are buried horizontally in the ground. Underground metallic water pipes can be used as grounding electrodes if they meet certain requirements. The NEC provides specific guidelines for the installation and sizing of grounding electrodes. These guidelines are designed to ensure that the grounding system is effective and safe. The size of the grounding conductor depends on the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding conductor based on the size of the service entrance conductors. The grounding conductor must be properly connected to the grounding electrode and to the equipment grounding system. The equipment grounding system is a network of conductors that connects all non-current carrying metal parts of electrical equipment to the grounding electrode. This system provides a path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse more quickly, clearing the fault. The equipment grounding system must be properly installed and maintained to ensure that it is effective. Regular testing of the grounding system is essential to ensure that it is working properly. Ground resistance testing can be used to measure the resistance of the earth to the flow of electrical current. This test can help to identify problems with the grounding system, such as corroded connections or broken conductors. Ground impedance testing can be used to measure the impedance of the grounding system at different frequencies. This test can help to identify problems with the grounding system that may not be apparent with ground resistance testing. Visual inspections of the grounding system should be performed regularly to check for any signs of damage or corrosion. Any problems that are identified should be addressed promptly. Firstly, there is soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is ideal for grounding, as it allows fault current to flow easily to ground. High soil resistivity, on the other hand, can impede the flow of current and make it difficult to achieve a good ground connection. Secondly, there's moisture content. Moisture content also affects soil resistivity. Moist soil is a better conductor of electricity than dry soil. Therefore, grounding electrodes should be installed in areas where the soil is consistently moist. Thirdly, there's temperature. Soil temperature can also affect soil resistivity. Cold soil is generally a poorer conductor of electricity than warm soil. Therefore, grounding electrodes should be installed below the frost line to ensure that they are not affected by freezing temperatures. Fourthly, there's chemical composition. The chemical composition of the soil can also affect its resistivity. Soils that are high in salts or minerals are generally better conductors of electricity than soils that are low in these substances. Fifthly, there's soil compaction. Compacted soil is generally a better conductor of electricity than loose soil. Therefore, grounding electrodes should be installed in areas where the soil is well compacted. Sixthly, there's the proximity to other underground utilities. The proximity of grounding electrodes to other underground utilities, such as water pipes or gas lines, can affect the performance of the grounding system. Grounding electrodes should be installed at least 6 feet away from other underground utilities to avoid interference. Seventhly, there's the presence of buried metal. The presence of buried metal, such as rebar or metal fencing, can also affect the performance of the grounding system. Buried metal can create a parallel path for fault current, which can reduce the effectiveness of the grounding system. Eighthly, there's the depth of the water table. The depth of the water table can also affect the performance of the grounding system. Grounding electrodes should be installed below the water table to ensure that they are in contact with moist soil. Ninthly, there's the type of soil. The type of soil can also affect the performance of the grounding system. Sandy soils are generally poorer conductors of electricity than clay soils. Therefore, grounding electrodes should be installed in areas where the soil is clay or loam. Tenthly, there are seasonal variations. Soil conditions can vary seasonally, which can affect the performance of the grounding system. Ground resistance measurements should be taken at different times of the year to ensure that the grounding system is effective. Grounding ensures safety by providing a low impedance path for fault currents, which helps to quickly trip over current protection devices like circuit breakers and fuses. This minimizes the duration of electrical faults, reducing the risk of electric shock, fire, and equipment damage. Bonding, on the other hand, connects all non-current carrying metal parts of electrical equipment and structures to create an equipotential plane. This minimizes voltage differences between conductive surfaces, reducing the risk of electric shock if someone comes into contact with two different metal parts simultaneously. The NEC provides specific requirements for grounding and bonding in various applications. These requirements are designed to ensure that electrical systems are installed and operated safely. Grounding and bonding are essential for protecting people and property from electrical hazards. Neglecting these practices can have serious consequences, including electric shock, fire, and equipment damage. Proper grounding and bonding techniques should be used in all electrical installations. Regular inspections and testing of grounding and bonding systems are essential to ensure that they are working properly. Grounding rods come in various lengths and diameters, typically ranging from 8 feet to 10 feet in length and from 1/2 inch to 3/4 inch in diameter. The choice of rod size depends on soil conditions and local codes. Grounding conductors, also known as equipment grounding conductors, provide a low impedance path for fault current to flow back to the source. These conductors are typically made of copper or aluminum and are sized according to the size of the circuit conductors. Bonding jumpers are used to connect different metal parts of electrical equipment and structures to create an equipotential plane. These jumpers are typically made of copper and are sized according to the size of the largest circuit conductor. Ground clamps are used to connect grounding conductors to grounding electrodes, such as ground rods or water pipes. These clamps must be made of corrosion-resistant materials and must be properly installed to ensure a good electrical connection. Grounding bushings are used to provide a smooth, rounded surface for grounding conductors to pass through metal enclosures. These bushings help to prevent damage to the grounding conductor and ensure good electrical connection. Grounding lock nuts are used to secure grounding bushings to metal enclosures. These lock nuts must be properly tightened to ensure a good electrical connection. Grounding washers are used to provide a larger surface area for grounding connections. These washers help to improve the electrical connection and prevent corrosion. Grounding screws are used to secure grounding conductors to metal enclosures. These screws must be made of corrosion-resistant materials and must be properly tightened to ensure a good electrical connection. Grounding lugs are used to connect grounding conductors to equipment terminals. These lugs must be sized appropriately for the conductor and must be properly installed to ensure a good electrical connection. Grounding connectors are used to connect grounding conductors together. These connectors must be made of corrosion-resistant materials and must be properly installed to ensure a good electrical connection. Always consult with a qualified electrician or electrical engineer to ensure that your grounding system is properly designed and installed. This is especially important for complex or critical electrical systems. Regular inspections and maintenance of the grounding system are essential to ensure that it continues to function properly over time. Ground resistance testing should be performed periodically to verify the effectiveness of the grounding system. Any problems that are identified should be addressed promptly. Proper grounding and bonding practices are essential for ensuring electrical safety and protecting people and property from electrical hazards. Do not take shortcuts or compromise on safety when it comes to grounding and bonding. If you are unsure about any aspect of grounding or bonding, consult with a qualified electrician or electrical engineer.